Welcome everyone to the MODBUS webinar. My name is Jason Lettieri and I'm sitting here with Anthony Nicolaitis as well. We are part of the Unitronics support team in our Quincy, Massachusetts office. Today I'm going to be doing the presenting for MODBUS, and Tony will be answering any questions that you may have. So feel free to just type those into the question box, and he's sitting here to answer anything that you may have questions about during the course of the presentation. So we'll start off with a PowerPoint. We're going to be looking just a little bit about MODBUS history, some general operation, talking about the slave addressing, and then some of the delay times that we recommend as well. So the MODBUS protocol, it's a messaging structure that was developed by Modicon in 1979, so it's been around for quite some time now. And it's used to establish a master-slave relationship between intelligent devices. So you can have a Unitronics controller be a master, and then also Unitronics controller be a slave. And we also support talking to other third-party devices as well. So it's not just solely Unitronics communication. It's very powerful because, as it says here as well, it's a de facto standard. So it's open and it's widely used in the industrial manufacturing environment. Some common examples would be customers would want to talk to other types of controllers, like an Allen Bradley, for example. You can also talk to any type of third-party HMI screen, or also any other types of I/O points. So that's just some quick examples of other types of devices that you can talk to. But it's really, as I said, an open standard, so you can talk to pretty much any device that supports the MODBUS protocol. We would be able to talk to that either as a master or as a slave. Unitronics can support being either of those on the MODBUS network. And let me just say real quick too that we have a master-slave relationship. And today we're going to be looking at MODBUS RTU, which is MODBUS serial. We also support MODBUS TCP, which is over the Ethernet layer. We're not going to be looking at that so much today. We already covered that in an earlier webinar on Ethernet. So if you are curious about MODBUS IP over Ethernet, you can take a look at the previous webinar that we have for that. But today we're going to be focusing on MODBUS RTU, MODBUS serial, and we support that over the RS-232 or also RS-485 network. It's more common to be using the RS-485 since you can have more nodes than you could on the point-to-point RS-232. But this graphic here shows just some of the basic operation for it. You have your master and your slave PLC configured. You will need to have a COM initialization block, a MODBUS configuration block, and then also any read coils or write coils or write registers, preset holding registers on your master device. And the master is really the controller which will be executing all of the commands. So your reading and your writing is all taking place from the master, and that's what you program into your ladder logic. Setting up a slave on the Unitronics network is really pretty simple to do. It only requires 2 nets in actuality. You have to have the same COM initialization to initialize your serial port to say whether it's 485 or 232. And then also a MODBUS configuration block so that port knows to talk serial protocol. And then the second net that you would have to have is the scan block. So the scan block, once you've configured the controller as a slave, the scan block is going to allow you to have the PLC be scanning and looking for requests for reading or writing from the master. So the slave is really just sitting there and waiting for requests from the master controller, which actually contains the logic to be able to read and write and find out whatever information that you want from the slave controller. So when we talk about the scan block for the slave controller, something we have to take into consideration is the slave addressing. Any device that you acquire that's a MODBUS slave will publish a MODBUS slave addressing table. These screenshots here are a quick example of the slave addressing table for Unitronics controllers, but like I said, any other type of third-party device will publish this table for their specific addressing points for their registers or their different options to be able to grab information from will be published in the slave addressing table. And you can see with Unitronics, This screenshot here, I should point out, is an example from the Enhanced Series Controller Slave Addressing Table, which is different from the standard series controllers. So let me just recap that. On Unitronics ends, the Enhanced Series controllers, which are your Vision 130, your 350, 570, 560, and 1040, I believe I named all of those, are the Enhanced Series controllers. And any of the standard series like the 120 or your 200 series or your M90 even, or your the older ones use different slave addressing tables, but in our help file is where I grabbed this information from. So the Enhanced Series controllers, the color screens, do have different addressing schemes than the standards, but it's all published in the help file if you wanted to reference back to those again. But as you can see here, if you're addressing a memory bit, for example, the pointer starts off at 0, so there's not a whole lot to actually calculate. 0 hex would reference your MB0 if you wanted to do a read or a write. 1 hex would be MB1, so on and so forth. And this table also shows you it's useful which type of command number that you're going to be using. The command numbers that you can see here, number 1 is for the read coil, a 15 is for the force coil. These number commands are not something that's just been developed by Unitronics. The command numbers are also published in the MODBUS standard. So, I mean, generally, if you're reading any of these types of coils that we have, the discrete values, it will be either a 0 or a 1 for the read, or the force coils for the reading and the writing. When you move into the registers, the most common that you'll be seeing is the number 3 command or the number 16 for the read holding register or the preset holding register. Again, this is the type of command that we will use to be able to read and write to our memory integer values, also our memory longs, or if we wanted to access system integers, for example, or any of these types of numeric values. Generally, you'll be using the number 3 command. There are some exceptions if you wanted to read floating points. We do have a different MODBUS command number for that. But again, this is all available in the help file, and we'll be looking at an example shortly where this will probably make a little bit more sense. But the main thing to point out here is that each of the registers have their own unique slave addressing, which is what you'll be targeting within the ladder logic function blocks to go out and target the MODBUS address. So you just have to make sure you know the equivalent hex address value from the slave address table that corresponds to the register type or the operand type that you want to be accessing. Now I should just point out too, when you're using MODBUS RTU, our serial MODBUS protocol, we do recommend that you have a delay time between consecutive references to the slaves. So if you have multiple slaves on your MODBUS network, we recommend that you insert some sort of, you can have cascading timers or some sort of timer regiment so that you delay the commands between the preset holding registers or the read coils or read holding registers. We just recommend basically that you have some sort of delay between those commands when you're referencing multiple slaves. And these numbers, again, was just taken from the help file. If you're using a 350 or the 570, the minimum is really 0. I'm sure this also corresponds to our 560 or our 1040 since it's the same hardware, essentially. But if you're using one of the higher-end controllers, I guess I'll say, the minimum time required is 0. Recommended is still 5 milliseconds. But you can see as the controllers progress down as far as power, the recommended time in between those slave references is increased as well. So that's just something to keep in mind to make sure you have enough delay time between your different command numbers. And this is essentially to make sure that you're not missing any reads or writes or having any data being lost due to overwriting or functions not fully completing in between the command sends. So you just have to make sure you have enough delay time in between those slaves, which again is published here and in the help file. And that's all that I have for the overview here. Now we'll take a look at an actual demo, and then we'll look at the code behind it. So I already have 2 programs, a master and a slave, loaded into 2 570 controllers on my desk here. And I'll hit my run. And again, I'm using the remote operator tool. And this just allows you to be able to remotely operate your controllers as if you were standing in front of them. But I'm mainly doing this so you can actually see what's going on in front of me on my desk. But if I go to the master and I enter a value to write, so I'm going to enter in 1, 2, 3, 4, and hit enter. Now, when I hit the write button, you should see the MODBUS slave value change. So the MI20 is what I had written to from the MODBUS master, and that appeared in the slave as soon as I hit the write button. Same thing if I change the value in MI10 on the slave. Let's make it 4, 5, 6, 7. I'll hit enter. As soon as I hit the read button on the MODBUS master, it's going to read in that value from MI10 and place it inside the master MODBUS controller. So once I hit read, the value will appear on the MODBUS master. And right now I just have a serial cable, just an RJ11, standard telephone cable plugged in between the two ports of the controllers. Just for a simple demo here, it's just on RS-232. And if you want to do a test, it's quite easy to do yourself as well. If you just have two controllers, you can use a standard telephone cable to plug in between the ports. Once you've downloaded the application, you can plug it in, and you can just demo and troubleshoot or debug any type of the MODBUS communication. But this is just a simple example of what you can do with a MODBUS master and slave application. So we'll go ahead and take a look at the logic behind this. So I have open right now the MODBUS master. You can see from the HMI, it's the program that I had just had pulled up in Remote Operator. But we'll go through some of the code right now. I believe we mentioned this before in our other webinar series. It's a good idea to always start off your program in net1 with a system bit 2 power-up condition. Again, this system bit 2 is active for only one scan when you turn on the PLC. So if you cycle power, as soon as the PLC boots up, anything after this system bit 2 contact will be high for one scan, and anything after it will be active for only one scan, which is really all that you need to have as a condition for any of your configuration parameters that you set up, whether it's the PLC name or if you're doing Ethernet, any of the TCP/IP card settings or Modbus settings or any sort of protocol that we talk. Any of those conditions just need to be a one-time power-up scan. So I have in my net1 the PLC name. Again, it's always a good idea to have a PLC name if you're looking to use any of our other remote utilities or accessing the SD card, for example, or remote operator. You will need to have a PLC name. Again, you can find the PLC name under the COM menu, and that's set PLC name. And within there, you can just type in a string. It can also be indirect, but most commonly you just type it in, and it is case sensitive, which is important to point out. So that's a standard function block that you want to have in almost all of your controllers. The second thing we have in series is the COM initialization block, and I'll show you. You can find that under the COM menu, and then COM port, and then init for initialization. So that's where I grabbed that from, and we'll open it up and see. Within the COM initialization block, we have a few different parameters that we can define. The first one is the COM port, and I'll click that down, and you'll see we have the option of COM 1, 2, and 3. Now it's important to point out that these COM 1, 2, and 3, these are referring to the physical ports on the side of the controller. It's not to be confused with the software port number that Windows assigns. If you're using, for example, a USB to serial adapter, you'll notice you may have COM 7 or 6 or 5 or 4 assigned in Windows, and that's the port that you pick in the communication and OS settings for VisiLogic when you want to download a program, for example. But the COM port numbers, you'll see it only goes up to 3. That's because it's referring to the maximum number of COM ports that you can have. For example, on a 200 series or a 500 series, you can have up to 3 COM ports. So that's why we have COM 1, 2, and 3. In this case, I had selected COM2 because I have, in this case, the serial cable is plugged in between my two controllers on COM port 2. Baud rate, you just need to make sure that you match the baud rate on both COM ports for both controllers, and this will most likely be a spec that is given to you if you're using any type of third-party device. Some may only talk at 9600, some may talk at 19,200. It's just important to make sure that you match the baud rate, and if you're using Unitronics controllers, you can actually use the maximum. I just had it on 57K in this case, but it's not really so relevant. You just have to make sure you match them between your different slave devices on the serial network. The standard, I have it selected as RS-32 in this case because I'm just a point-to-point, but if you are actually more likely scenario having multiple slaves on your Modbus network, you're going to want to use the RS-485 option, which allows you to daisy chain multiple controllers together. We do have an adapter available which allows you to daisy chain more than one serial port. So you have a serial port, it comes out and expands into two ports, so you can actually daisy chain over the RS-485 network. The other options here are really, again, you just have to make sure you match them between your specified device parameters from the third-party device. The most common is 8, 9, and 1 for your parity, or your data bits, your parity, and your stop bits. 8, 9, 1 is the most common, but if you do have a device that is different, you have the option to select to make sure you match them. RS-232 timeout, you can leave that at the standard half a second. And that's all that we really need to define within this COM initialization block. If we're using a modem, you'd want to select under here, but that's another topic for another day. In this case, though, we'll just leave it as none. We have our COM port defined, our parity bits, and our standard RS-232. And that's all that needs to be in here. Now, Modbus config block, this is what's telling us that we want to be able to talk Modbus over this COM port 2 that we just defined. So I'll show you. You grab this block from the function blocks menu, Modbus, and then configuration is this first one that we have in the last block in net 1. I'll open it up. You'll see you have the option to define it a name. Modbus 1 is what it's named as default, but you can give it any sort of name that you like. Within the block here, you have to again specify that you're going to be using port 2 for Modbus. So we just defined the settings for port 2 in the COM init block. Now we have to tell the Modbus configuration block that we are going to be using port 2. In this case, again, you can see you have 1, 2, or 3 for the 3 available maximum COM ports. We're using COM 2 in this case. Network ID. Each controller on the Modbus network has to have its own unique network ID. And you can see if you drop down, it ranges from 1 to 255 are the available options. So if you're using an RS-485 network, I believe the network ID starts at somewhere around 40 as a valid network ID, but it's just important to make sure that each device on the Modbus network has its own unique network ID, because that's how we're really going to be addressing and telling that's how the master goes out and finds its slave devices. You target it for the correct network ID. So in this case, we made our master be network ID 1. You'll see later that the slave in this demo that we have is defined as network ID 2. But our master is 1 as defined in the Modbus config block. Timeout and retries. The default is 103. You can generally leave it as that standard. And then the last option under the out parameter is a memory bit. You want to make sure you assign a memory bit here, which is going to be your function in progress bit. So this bit is going to be high whenever a command is currently being sent or some action is currently in progress, as the name denotes. So you use this just to make sure that you don't override any communications that are currently occurring. You can use this function in progress bit to make sure that doesn't happen. So in nets 2 and 3 is where we're going to actually be going out and reading MI10 from our slave device. You can see we have it in a 2-net structure here, which is generally what we would always recommend whenever you're doing any sort of communications parameters, to have this, we call it a set hold routine, I guess, or latching routine. But essentially what we're doing, when you press MB1, the request to read, this was just a button on our HMI MB1, but the positive transition of that button for the read on the HMI, we're going to set a next available memory bit, which in this case was MB3. So as soon as we push the button, we're going to set MB3, which goes down and is the enabling condition for net 3. So the reason we do this is if, for example, we push the read button, and if that exact instant that we push the read button, another Modbus command was occurring, it wouldn't be able to read that. So the fact that we have a 2-net structure, this latch and hold, when we press the read button, it's going to set MB3. It's going to have MB3 be set and waiting to read until we successfully read. So you can notice we reset MB3 at the end of the net. So we push the button, we set the read command, we try to keep on reading until we have a read that's been finalized and the function block has actually been executed. That is when we reset the MB3 enabler. So again, this 2-net structure is something you can follow in any of your programs really, but it's just to make sure that your communication blocks actually do execute. So to ensure that you do have your data being read or written, make sure a successful transmission does occur, you can have this set and contact and then read the set hold command that we call it this 2-net structure. So we have in net 3, as I just explained, the MB3 to enable the read, and we're also using our MB2 function in progress, which was defined in the Modbus configuration function block. So we're saying if it's currently low, if there's no function currently occurring, if nothing is in progress, then we're going to go ahead and perform our read holding register number 3 command. And you grab this read holding register command from under the function block menu, Modbus, and then you'll see all the different number commands, the Modbus standard numbers, which we support. We're going to be using the read holding register. Number 3 is just the one that's been grabbed down here, but you can just see the different options available as well. So I'll open up the Modbus read block, and then we'll talk a little bit about what we have going on here. So there's a couple parameters to define. First one is the slave ID. So the first parameter is really saying where we want to go out on the Modbus network and perform this read command from. So we only have 2 devices in this example. We just saw that the Modbus master was configured as slave ID 1, and our slave is defined as slave ID 2, which we'll look at a little bit later. But you can take my word for it now that we've defined the slave controller as slave ID 2. When you open that block, you'll see, just like we defined earlier, you have the option to select your different slave IDs. Now, the start of vector. This is where you enter in the address that you want to be able to go out and read from. Here it's a 10. We're going to be reading MI10 like we saw on the slave screen before. But you'll notice that nowhere in here do we define MI10 or memory long 10 if we wanted to read a memory long. What we actually have is a pound sign, which denotes a constant, and then a number. So we're just entering 10 here, so we're sending out, Modbus doesn't know anything about memory integers or memory longs in Unitronics nomenclature. Modbus just really cares about addresses. So we're really just going to be looking out for address 10 on the Modbus network in this case. And again, the address 10 we saw from the slave address table under Enhanced Series Controllers. The offset for memory integers starts at 0, so MI10 is just going to be a 10 decimal value or an A in hex if you wanted to convert it. But that's why we have a value of 10 entered in on the program there. I'll show you if you want to convert. It's easiest if you open up the calculator from Windows. In Windows Calculator, when you have it set on scientific mode, standard mode doesn't have too many options, but when you set it on scientific, it allows you to see now you can convert between decimal or binary or hex is what we really care about here. So if, for example, we want to address, let's say, memory long number 32. So you can see that the offset for memory longs starts at 7,000 hex. So that means what we need to do is figure out what memory long address 32 is in 7,000 hex offset, essentially. So the way that you would do that is you can start off by clicking the hex value in the calculator. Then I'll enter in my 7,000 hex. So I have my 7,000 hex, which equates to my memory long 0 in this case. So I have my 7,000 hex, and I can't just add 32 here because a 32 hex is different than a 32 decimal. So what I have to do is convert this 7,000 hex over to decimal first. So this 28,672 is equivalent to 7,000 hex, or also memory long 0. But we want to find out, in this case I just said, for an example, memory long 32. So what I'm going to do now is add 32 decimal to that 7,000 hex, or 28,000 or so decimal. So this 28,704 is equivalent to my memory long 32 value, which is 7,020 in hex. So again, I'll do that one more time. I have my 7,000 hex. First thing I do is convert it over to decimal. So my memory long 0 is equal to 28,672, but I'm looking for memory long 32, so I'm going to add my 32 decimal. So this 28,704 is my memory long 32. If I want to look at that in hex again, I just click back to hex and I get my 7,020. You'll notice if I do a number, for example, like 7,001 hex, convert to decimal, you can just keep doing any of these really. I won't go through it again. But that's how you just have to make sure you calculate your hex value, which is what we had entered in back in our read holding register. So you do have the option of dropping down and picking a hex. You'll see it switches to A. You can enter in this value in hex or also in decimal. So the main thing is that the second parameter is your start of slave vector. This is a slave address that you're pointing to. In this case, MI10. Since we're using a memory integer, offset starts at 0. You can just enter in 10 and be able to read that value. Now the read vector length is specified as 1 in this case. So this is really just saying that we're only going to be reading address location 10, which is also equivalent to memory integer 10. If I had made this at 2, it means we're going to read memory address location 10 and 11, which corresponds to memory integer 10 and 11. So you can just read multiple registers if you increase the read vector length. Master start of vector. Now this location is where we're actually going to be placing the value that we went out and read, and it's saying we're going to store it now in MI5. So we went out, we read our address location 10, MI10 you can say, and we're going to be placing that value that we read into our master slave start of vector MI5. So MI5 is where the value that we just read is stored locally on the master device. And then what else we have here is really just a couple of status. We have 3 different status operands that we could check out. MI0 is our status message, double word 0 is our sessions, and double word 1 is our acknowledgments. We'll take a look. If you click help on any of the commands, you'll see it brings you right to the correct spot in the help file. And what I'm looking for is our MODBUS status operands. Let me just make this a little bit larger. So the value that we have in MI0 in this case If you have a 0 in MI0, it means everything is good. Your status is okay. Some possible numbers you could be getting in there is a 0, 1, 2, 3. It really just helps you try to debug and troubleshoot your application if your master is timing out or you have no communications or an illegal address. Any of those Modbus status messages will be placed in the number, and then you can see the equivalent number and a description of the error from the help file that shows your Modbus status operand. So you can always open up the help file and be able to go in and see what those statuses correlate to. Now the sessions and the acknowledgements. Those two integers, or double words I guess in this case, are particularly useful if you're trying to see if a message is sent out, but if you're not receiving it. The total sessions will always show the number of read commands or write commands that have been issued. They've been sent out of the controllers. And then the second parameter, the acknowledgements, should come back and tell you if it was successfully read or accepted. So basically you want your sessions to always equal your acknowledgements. If you are reading and writing and successfully acknowledging without error, your sessions and your acknowledgements should match. If there is a difference between them, that will generally mean that some data is being lost. Sometimes it's because you're polling it too frequently or other extraneous issues, but you can check your status message and also your sessions and your acknowledgements to troubleshoot. If you feel like you're losing data, you can use these three different status and session and acknowledgement operands to be able to troubleshoot and diagnose your system. And you can see we have pretty much the same setup in nets 4 and 5 for write. Instead here we're using a Modbus command number 16. Our Modbus command number 16, which is our preset holding register, grabbed from the Modbus menu. We have our same set hold routine in our 2-net structure. And if I open this up, you'll see again it's almost identical. You need to specify your slave address, so we want to go out and write to our slave ID number 2 on the Modbus network. Our start a vector, address 20, again, which correlates to MI20. So you just enter in the Modbus number for the address that you want to be able to read. In this case, we're reading 20. Our master vector, start a vector. I don't know why this got changed. But our master start a vector. Wait, what is going on here? Oh, okay, yeah. It has an incorrect label on it. But we have our slave start a vector, and then the master start a vector is where we're going to be placing it, and then again the vector length as well. So the same sort of parameters as before, as well as the status messages and the total sessions and acknowledgements. So are there any other questions on the Modbus master? That's really all that you need to have for the Modbus master. Again, you'd want to insert any of the read holding register commands or the preset holding registers for your specific system, addressing whatever operands or values that you're trying to read from your slave device. Okay, so we'll look at the slave program next. So you can see there's not a whole lot going on in the slave program. Same as the master, we set up our PLC name, we set up our COM initialization block, also our Modbus config. In this case, you can see we're also using port 2, but the network ID is 2, which is why in our master application we were targeting our network ID 2, we were targeting our slave, which you can see here is defined as network ID 2, and just the standard units of time for 100 and 3, and our memory bit function in progress, which really isn't used, the function in progress, in the slave application, but you still define it anyway. So the main thing to make the slave program work and make it tick as a slave, what you want to have is the MODBUS scan EX block. So this block, you'll see there's nothing to define in it. If I click it, nothing opens up. You just have to make sure you have this placed down against the rail, and it's going to constantly be scanning and constantly be looking for commands that are being issued from the master device, and it's going to be allowing the master to access its registers by having this scan block. And the scan block is found under function blocks, MODBUS, and then scan EX is the one that we're using. You can see there's a couple different versions here. We have scan EX, scan 32, and scan. Now, what are the differences between them? Generally speaking, you'd always want to use the scan EX block. It's the most up-to-date block that we have. If you had an older application, I believe it was between like MODBUS or 2.0 or basically earlier programs, you'd want to use, for example, the scan block. So you just use the other ones if you have an older application. And I think it talks about it in the help file as well under the scans. MODBUS scan, yeah. So it explains the scan and scan EX. It's really just for older applications. You'd want to use the regular scan, but for most of them, scan EX will be sufficient. It'll suffice. It's the one that you want to use for most applications that you will have the scan EX. Placed against the rail is all that you really need for the slave address, for the slave to be able to tick. And I mentioned you can also find it under the help. And then it is a little bit hidden, but it's under ladder. And then FB's library, communication function blocks, and then MODBUS is where I had been grabbing all of this information from. You can see there's also a separate tab for MODBUS IP, but all of the function blocks and command registers are essentially the same. So if you can program a MODBUS RTU, there's not a whole lot different to be able to program MODBUS IP. You're just really using the Ethernet as your physical medium instead of the RS-485 or RS-232. Now I was talking earlier about 485. Our help file also explains our different 485 options that we have. And this is what I was looking for. Network and wiring topology. This shows you how you can wire up your network to be 485 and have multiple nodes on here. I mentioned earlier about an adapter that allows you to have the daisy chaining. The part number is available here as well. It's the MJ1022CS66 is the one you want. But the graphic explains a little bit better. You have just the RJ11 that plugs into the side of your controller, and then it goes out and allows you to wire up your RS-485 as a two-wire connection. So it allows you to splice in essentially and daisy chain each node, each network ID on your RS-485 network. So all the information that you would need to have about RS-485 actual physical wiring for MODBUS, again, is available under the communications, and then your 485 options and about RS-485, and also the network topology explains pretty well here for more reading later on if you were wondering about how to actually set that up. And if there's no other questions, that's all the material that I have prepared for today. I want to say as well that we are having all of our webinars. They're going to be available online. We have a bunch that are available online already. If you go to the main Unitronics page, we have them in two places. Under the Support tab, you'll see we have a webinar section where you can go through and see some of them as well. Or if you hop on our forum, which is just forum.unitronics.com, the most recent one is generally the first thing that pops up when you go to our forum. In this case, the SD cards was the last one that we did about a week or two ago. But if you click on Webinars Collection under the blogs, you'll see available as well are the different ones that we have. And just as an example, you can see we have the YouTube videos for the recorded webinars, also any questions or answers, and attached files. So the recording of today's webinar will be available online here, so you can go back and review any of the points that you had or any questions. Any questions anyone asked will be available here, as well as downloading the two master and slave applications that I demonstrated and walked through today. Those will be available shortly online, so you can go back and download those as well. So in those two locations on our website. And if there are no further questions, I'd like to thank everyone for attending. And again, I'll leave the webinar open for a short while longer to field any other questions that people may think of and want to type in and answer. But otherwise, thank you for attending and have a nice day.